Hello everyone, welcome back. So this is going to be our third part of our energy series. So really quick, before I go on our previous video, which the link should appear somewhere here soon, I made this case, and we're going to be talking about it too, where there's a box of a given mass. However, I didn't give you the mass, so that was my mistake, and I apologize for that. But I wrote it down in the comments. It's going to be 5 kilograms. Our height is 10 meters. Goes down a ramp. And then it comes in here. There's a spring here, right, attached to a wall. This box crashes into the spring and moves it at a distance x, and we try to find our distance x, right? So if this doesn't sound familiar or you forgot, go back to our videos and check it out, please, because this is just going to build upon that concept. So now we're going to treat friction. All right, so now we have this rough surface right here. It doesn't necessarily have to be sticks or anything, but I'm just saying this symbolizes that there's friction there in our case, and it's going to be a 3-meter path, and the coefficient of friction, that would be mu sub k, is 0.25. all right, now the same question the professor would ask you in an exam: how much does this spring compress, the maximum that it compresses? All right, so now this is where I was saying that breaking it down into different parts comes in handy, because we're going to say conservation of energy, energy initial equals energy final, and I'm just going to copy from our previous video. Again, please check that out if you don't know what I'm talking about. So first, let's call this V1 at the bottom, right, because the box will be here eventually, so this will be V1. And then after it crosses the friction, it will be V2. So initially, it only has potential energy because it's only at height, it's not moving, right? So then it's only potential energy, which would go into all kinetic energy, right? At the bottom of the hill, right here, our V1. So that would mean mgh equals to 1 over 2 mv1 squared. Masses cancel out, right? And now, from our previous video, V equals 14 meters per second. All right, so now that's V1. Okay, so now we're going to say, all right, how do we take friction into account? Like that, I didn't think friction was an energy conservation. It's actually not. Energy is wasted once it goes through there, and it will transform into heat. Usually we say that energy gets lost as heat. So same thing here. We're going to say that energy initial, and when I say energy initial, it will mean this energy. So if you want to label it, if this will make it easier for you, we can do this, right? So energy 1, energy 2, right before it goes in. This would be energy 3, right? And then this would be energy 4, I believe. I apologize, somebody just got in the room. All right, so right here, this energy would be energy 2, right? Energy 1. So this will be energy 2 going into energy 3. And then in our energy 3, we have velocity, and we lost some part of energy as friction, right? So here, what we're going to say that initially, right here in E2, it was only moving, right? Completely plain, so it was all kinetic energy. And it finished as kinetic energy 2 because it got out and it kept moving, right? Kinetic energy plus our energy lost as heat, and heat done by work from the friction, right? So now here we're going to say, all right, this is going to be 1/2 mv1 squared equals to 1 over 2 mv2 squared plus work done by friction. So that will be force of friction times distance from our video of work. All right, so now we're trying to find V2, the velocity that is exited out with this, right? So let's move this to the other side. 1 over 2 mv1 squared minus force of friction times d equals 1 over 2 mv2 squared. All right, now let's multiply by 2 both sides to get rid of this right here. Multiply by 2 the whole thing, and then divide by m, right? Alright, so then we end up having v squared 2, so right after it gets out of that friction, is going to be equal to, if you do FOIL right here, right? So then this will be mv1 squared minus force of friction times distance over mass, right? So now remember from our previous videos as well, we know that the force of friction in a horizontal, we know that that's nothing else but mg times mu sub s or k, but in this case it's already moving, so it's going to be mu sub k, which we're given, times the distance, right, divided by m. Notice how everything has an m, so you can factor it out, or you can just say all m's cancel out, which ends up giving us this very nice looking formula, which would be v1 squared minus g times mu sub k times the distance. And that would equals to your v squared 2. Alright, so now we're going to keep doing this, and now we're going to say, I'm just going to move forward instead of downward, because that would probably be our part 2. Actually, I would just move downward. Alright, so now here v2 squared is going to be equals to v1 squared minus g times mu sub k times the distance, which we all have those values. v1 would be the 14 meters per second, g is 9.8, the kinetic coefficient of friction will be 0.25, the distance is the distance traveled over friction, which is 3 meters, and then you take the square root. So now v2, please pause the video and make sure you get the numbers we're getting. I get 13.46 meters per second. Notice how the change is kind of small, very insignificant, but professors like to test you and see if you have an understanding and if you can do the math. So just go ahead and do it. Pause the video, watch it as many times, ask for clarifications if you guys need that. Alright, so V2 is 13.46. Alright, so that is right here. This V is 13.46 meters per second. Alright, so now that is going to go into our E4, which is into the spring. So now, to keep that going, we're going to say E3 is going to go into E4, conservation of energy. Now in E3, again, it's just moving because we already taken into account the coefficient of friction, so it's right here. It already went through the friction. Now it's about to crash into our spring and compress it, so then it's all kinetic initially, and then it's all going to go into potential energies from our spring, just like it did in our previous video. So now we're going to say 1 over 2 mv squared equals to 1 over 2 kx squared. The 1/2s cancel, divide by k, take the square root like we did in our previous video, right? And that gives you x. Okay, now pause the video, plug the numbers in. This time I did give you the mass, it's 5. I'm sorry for not giving you the mass earlier in the previous video. So pause the video, k is 500, which I didn't give you in this case. I am so sorry for that. K is equals to 500 newtons per meter. Alright, I apologize for leaving that out. But I believe you now have all the numbers that you need. So I end up getting x equals to 1.346 meters. And our previous one was actually 1.4, so there's not a significant difference. However, there is a difference, and professors like to test you on this. They love testing you on this. So just know how to get this. Actually, I just tried this E1, E2, E3, E4 on this video. I completely didn't write that out as I was planning this lecture. So let me know if it works out for you guys. Comment below, and like us on Facebook, subscribe on YouTube, and check out our website. So good luck with your studies. Remember, let us know how we can help you because we're here to serve. Good luck.